Sheldon, how can a star like Stevenson 218 be over 2,000 times the sun's radius and still hold itself together? Wouldn't gravity just make it collapse, or is there something special about stars that big?
Excellent question, Penny. Stephenson 218 is a red supergiant, one of the largest known stars, and its massive size is maintained by a delicate balance between gravity pulling inward and the tremendous outward pressure from nuclear fusion in its core. At this scale, the star's outer layers are so diffuse that its average density is far less than air. In fact, if you stood in the surface of Stephenson 218, you'd barely notice any resistance. The core is hot and dense enough to fuse elements beyond hydrogen, and that fusion energy creates enough outward pressure to counter gravity, at least until the fuel runs low.
But if it's so enormous and spread out, what keeps it from just flying apart or collapsing faster than smaller stars do?
The answer lies in hydrostatic equilibrium and the star's mass loss process. Stephenson 218's immense mass provides strong gravity to hold its outer layers, but as its fusion rate accelerates, the radiation pressure in the outer envelope causes the star to continuously lose mass through stellar winds. The balance lasts only as long as nuclear burning can maintain it. When fusion can no longer compensate for gravity, especially as heavier elements are formed, the star's core collapses rapidly, leading to a supernova, a process far more chaotic and energetic than in smaller stars.
So does being that big mean it will explode more spectacularly, or does its size change how it ends its life?
Indeed, Penny. The fate of Stephenson 218 is set by its mass and fusion history. When the core can no longer support fusion, typically after forming iron, the collapse is sudden and total, triggering a supernova of tremendous scale. The star's gargantuan size guarantees that its end will be one of the most dramatic events in the universe, potentially producing a black hole and dispersing heavy elements across space. In short, its enormous size makes the final collapse and explosion even more spectacular, both in energy and cosmic impact.